All right. So my name is Samir. I am going to be your instructor for the first 50 minutes or so this morning. The most important thing to do right now is just to go to that first large blue link, tinyurl.com, DockerCon GenAI, and that will get you to this Google document. And this will be a way for us to share a lot of information with you today and a lot of links. For now, I would just log into Wi-Fi. You can start logging into some of the other stuff and opening up the slides, but you can also wait till we get to that part of the schedule. All right. So here is our agenda for today. We're going to spend about 45 minutes this morning doing a fast-paced lecture crash course on some of the generative AI models that my colleagues from OctoML are going to run through the labs with you later today. So notice that we got a crash course, then about a 10-minute lab prerequisite. This is really important to do before the break because there is a Docker build command that we'd like you to kick off that takes about 20 minutes. So that can be building during that 15-minute break at 9 a.m. So try to definitely get to that. And then Lab 1 and Lab 2 are essentially some of the most interesting part of today where you guys are going to build out a multi-modal generative AI application. All right. So for my part this morning, I'm going to really quickly fly through Stable Diffusion, Clip Interrogator, the Llama 2 LLM, a little bit about fine-tuning, a little bit about control net and face swap, and then jump into the 10-minute prereqs and initial lab. Keep in mind that we are going to be moving fast, so this lecture is really only meant to give you just enough intuition behind the models so that when Thierry takes over next, you're kind of comfortable with the concepts that he's going to be covering. All right, let's start with Stable Diffusion. How many people here have actually run a Stable Diffusion model and generated an image? Oh, OK, a few people. You're definitely going to do that today. Give me just a second to turn Slack off. All right, so Stable Diffusion. The first thing you might be wondering is you've heard of the term diffusion, I'm sure, from your high school physics classes. It's the spreading of something more widely, something diffusing. The 2015 paper that originally introduced these types of diffusion models had this long sentence that describes why the word diffusion was used that I highlighted here in bold that I thought would be interesting to start this section with. The essential idea is to systematically and slowly destroy structure in a data distribution through an iterative forward diffusion process. And then we learn a reverse diffusion process that restores the structure in the data, yielding a highly flexible and trackable generative model of the data. So what does that even mean? So the point of these models, what it's going to do is essentially use an encoder to get some latent representations and then convert those latent representations using a decoder. So what is that thing in the middle? What is latent space? That is, as you can see here, latent representations encode a meaningful internal representation of externally observed events by reducing the dimensionality of the input data into simpler representations. So in Stable Diffusion version 1, that latent space matrix in the middle was 64 by 64 matrix. In SDXL that we're going to use today, it's a little bit bigger. It's 128 by 128. But essentially, during the training process of this model, as you feed it images, it's trying to figure out what is the essence of this image, and how do I convert that essence of the image into a number matrix of 64 by 64 or 120 by 128. So you can think of it like extracting out those features from the original image and then compressing it to some extent into the hidden representation in the latent space. All right, so just kind of keep that high-level intuition in mind. Here's the crux of what's going on here, the magic. Stable Diffusion is essentially removing noise from images. So when you tell it to generate an image based on your text prompt, what Stable Diffusion does is it's like fed a randomly completely noisy image and your text prompt. It gets those two things. And then that noisy image has like no real data in it. It's just like Gaussian noise. So now Stable Diffusion has to clean up that image. It has to remove the noise to make the image, the final image, align to your text prompt. So in the training process, like when Stability AI and the team was creating this model, the model understood concepts of the world through the training data. And that is like essentially embedded into the model. So here's an interesting example. Here you can see like at the bottom, there's step 1, step 20, step 30, step 40, and 50. And as it's going iteratively through more steps, it's eventually emerging and creating this skeleton playing a guitar. So it's interesting here that the model has a concept of this artist Geiger's artwork along with knowledge of the world, like how a guitar is supposed to look when you play one. Like you kind of hold it like that. All right, so that's one thing to keep in mind. Like what Stable Diffusion is doing is it runs through a lot of steps, typically 30 to 50, and as it does more and more steps, it's like removing more noise from the image. These are the inference steps. Here's, for example, a denoising 25 times. So the prompt here could be, this is a super noisy painting of a, well, this is what it's doing. Here's a super noisy painting of an alien playing a guitar in the style of Geiger. Can you clean it up for me? That's essentially what you're asking Stable Diffusion and giving it, like I said, a completely noisy image to start with. So this model is obviously statistical based. It's estimating probabilities of what this image needs to look like in order for it to meet your prompt requirements. And it'll essentially statistically just keep moving forward to the highest probability space it knows to try to achieve alignment with that prompt. All right, so that's inference, right? Like that's the way you're going to use Stable Diffusion today. Give it a prompt, and in the background, a noisy image gets fed in, and it will align the final image. So what happens during training? Well, during training, diffusion models are progressively adding noise to an image so that they get a proper image, right, with no noise in it. And then the model starts adding noise to that image to wipe out all the details until it becomes pure noise. And then in the next part of the training process, it will learn to reverse that corruption process and resynthesize the image to gradually denoise it until it gets to a clean image. And that clean image it gets to at the end of that training step is supposed to look like the very original image before it destroyed the data in it. And that's how it kind of like figures out that this graphic aligns to this prompt. So obviously, like during the training step, you give it pairs of text prompts and clean images. Okay, so that's the intuition around how this works. All of these generative AI models have somewhere from like 10 to 20 parameters. Here are some of the important ones you might want to keep in mind for Stable Diffusion. There's a prompt. It's like 77 tokens. We'll cover tokens in a minute, but that's like maybe 50 words. There's also a negative prompt of what you don't want it to do. So you can give it 2 prompts, actually. SDXL defaults to a square, 1024 by 1024. One of the parameters is how many output images do you want it to create. You can usually send between 1 to 4. There are schedulers. This is the denoising algorithm. There's like 10 or 15 schedulers in Stable Diffusion XL. Number of inference steps, although you can set it between 1 through 500, you're typically going to see somewhere between like 30 to 50. After that, it's like diminishing returns. You're like eating up your GPU, but not getting a better image. There's a guidance scale. There is a seed for randomness. LoRa's are essentially a way to add styling and customization to the base Stable Diffusion model. It's part of a fine-tuning step that we'll discuss later. All right. Really quick timeline of some of the most popular image generation models. OpenAI, DALL-E kind of kicked off this in January 2021. Then there was next year, in July 2022, DALL-E 2. Midjourney, I'm sure you've heard of, also was July 2022. Stable Diffusion was essentially released August 2022 publicly. SDXL that you guys are going to use today in the lab is July 2023, and it's under a open source license. And actually, just a week ago or so, DALL-E 3 was also released from OpenAI. All right, so a little bit more detail that I'm going to fly through. Again, remember that like the goal here is just to get some intuition here. You're not going to become an expert in any of these models, but I just want you to have some sense before you play with the lab in about an hour. All right, high level, how does an image become a file? This image would convert into a file like this. This is the actual real numbers for this image. So 512 rows, 512 columns, RGB space, you might remember. So red, green, blue. And each one of those pixels is represented with a red, green, or blue amount of saturation, essentially. All right, so you got 3 matrices. How does a prompt, like a text, become numbers so a computer can understand it? Well, here's like a prompt, for example. Each word is converted into a vector of 768 numbers. And with this many words, you would get about 25,000 numbers. So that's a matrix or a tensor. Here's the architecture of Stable Diffusion, specifically for inference. So you send in some input text, a prompt, about 77 tokens. That goes through a encoder, like clip text, that converts that into essentially like embeddings or like a matrix like we talked about. Now, the random noisy image with Gaussian noisiness is fed in to this image creator, which is essentially a unit. It's a type of a convolution neural network and a scheduler. This is where essentially all the magic happens right here. This is the thing that runs 50, maybe 100 times. These are the steps. That's where diffusion essentially happens. This is what's removing the noise out of this image to align it to your prompt. And that's all happening with numbers, right? That's like messing with the matrix, essentially, of numbers. So then to convert that into an image that you can see, that tensor gets fed into an image decoder, which essentially converts it into a number. Sorry, into an image. All right, just the same graphic here. Notice that there's like a blue side and a red side. So that red side is essentially the image creator. The initial blue side was the text encoder. So diving a little bit deeper, remember there were 2 parts. The image creator, info creator, this is where the inference steps are happening, like usually like 30 to 50 is actually more typical. This is the diffusion process, step-by-step processing information that creates a high-quality image of the decoder. Image decoder is the very final part here that actually transforms the image from the latent, like compressed representation, which is 128 by 128 matrix in Stable Diffusion, and makes an image out of it. All right, this is a little bit more detail about the models that run inside this. You know, one interesting thing about Stable Diffusion, and actually most of the generative AI models, is that it's really like comprised of many models within it. You can see here, there's like a clip text, there's unit, and then there's a decoder at the end of it. All right. Let's continue here. This is just really showing the different steps until you get to the final image. All right. If you're new to Stable Diffusion, one thing you might find interesting is this is an article from The Economist, and this creator, this artist that they interviewed for this article said, the image I produce isn't my work. My work is the prompt. And to create this image, it took him hundreds of iterations with Midjourney. So it's interesting, like even on Reddit, I found this comment, this guy saying, I've been pretty stingy with my prompts. So like he doesn't like to share the prompts. So there's like one high level takeaway here, which is if you're an artist actually trying to get to an end result, speed of generation really matters. If you're like creating 100 images, like you probably don't want to wait like a minute for each image, like 3 seconds would be a lot better. And second, this is like actually really different than how the general public might use image generators in like Adobe Fire, the Fire product, right? I feel like a lot of the general public just types in a prompt, gets what they want. Artists are pretty different. They're like hacking these prompts iteratively, potentially as many as 100 times before they get what they want. So you might want to actually think about doing something in between, like try multiple prompts to try to get to your final image. It's not kind of like a one-shot approach. What do you actually put in these prompts? In Stable Diffusion, like 1.x and 2.x, there was this study done of like some of the analytics that they collected with like analyzing a bunch of prompts. But you can skim through this. You can put a subject in the prompt, the medium, like an illustration or photograph or a poster or concept art, the technique, a genre, mood, tone, lighting, resolution, artistic references, reception, or popularity. So just some ideas as you guys play with this in the lab of what you can put in the prompt. So Stable Diffusion XL was just released about a month ago. What's different about it? It has a lot more parameters. It's like anywhere between 3 to 6 times larger. Actually, it runs 2 different large models in it. So it's about 6.5 billion parameters, which is way bigger than the largest Stable Diffusion 2.1 model. And I'll let you kind of skim through this, but there's like a bunch of different, well, here you go. Here are the architectural changes in SDXL versus the older versions of Stable Diffusion. This is a screenshot from the SDXL paper that came out, I think, a few weeks ago. All right, so that's like some intuition about SDXL. One thing I'd like to do next is take a survey, an anonymous survey from everyone, just to get a sense of where everyone's like knowledge is on AI. This is going to help me decide how much depth to get into in the remaining like 30, 40 minutes, and also for my follow-up instructors to have a sense. So please go to that URL, tinyurl.com, DockerCon, GenAI-preclass. Please do this whether you're in person or online. It's totally anonymous, and I'm actually going to share the results of this with you guys in like a few more minutes, as soon as you guys are done with this. So we're all going to kind of see where everyone's like kind of knowledge is this morning. So there's really 2 links. You might also want to open up the class notes document link here at the bottom as soon as you finish that survey. All right, so in the background, I'm going to start looking at the results of the survey and see how many people have done it, and then we'll continue in just a minute. All right, I'm going to start reviewing these. And I think I might have to I'll wait till after I'm done speaking, and then I'll pull a PDF of this and put a link to it in the down here. Right, so I'll give you that link, or I'll give you the responses in just a second, in about 20, 30 minutes as promised. All right, 50 people. I think that's good enough to get a consensus. How much experience do you have with the field of ML in general? Fundamentals, beginner concepts. So about 75% of the people here say like kind of 0 or just kind of fundamentals. And about 7% would classify themselves as advanced. Which of the following, so I have a hunch what you guys would say here. Oh, actually, that's interesting. So most people classify themselves as a developer or a software engineer, as opposed to what I thought it would be, more of like DevOps or operations. Okay. How comfortable are you with programming in general, like medium or advanced? Okay, that's really great. How much experience do you have with the following models? I was very interested in this. So most people say like 0 knowledge. Okay. Background experience with image generation models, very new, 41%. Or have created some images with Midjourney, 30 people, 48%. So cool, we're at like 62 responses. That's great. About like 6 of you guys have made more than 100 images. That's cool. And what is your background and experience with large language models? 30% very new. I thought this was interesting. So half of you guys have had at least 5 conversations with ChatGPT. I have used at least one LLM that's not ChatGPT, 21 people, 32%. Wow, like 5 of you guys have actually fine-tuned a large language model even. And 1 person has used a vector database. After class, what are you guys going to do? Articulate how deep learning works. 50% install, configure, and administer deep learning clusters, write applications. So yeah, this lab that you guys are going to do is essentially geared for like writing applications and containerizing an ML model, SDXL. Cool. Anything else? Video recording is bad. Sorry about that. All right. There's not a Slack group, but we have a Discord for today, which you guys can see in this doc. All right. So I will put the PDF for the responses up there whenever I'm done speaking. And I'm going to kind of fly through the rest. Give me a second here. All right. So Clip Interrogator is kind of like a, well, I think it's best described by like explaining what's happening here. So it is essentially a way to understand what is in an image. It's almost like classifying an image. It's a new model, January 2021. It learns visual concepts and can be applied for visual classification. It's trained on image text pairs from the internet. So you can kind of see here like how it compares to a really famous convolutional neural network, or ResNet. And it's classifying like banana images, it looks like over there. So given an image, predict which out of a set of 32,000 randomly sampled text snippets is actually paired with this image. That's how the training of this was done. So there were a bunch of images and 32,000 text pairs. And in the training phase, when it's fed an image, it has to select one of the 32,000 text snippets correctly. That's essentially the training process. And then the model recognizes a wide variety of visual concepts and associates it with the words. Here, when you feed it an image of a guacamole, it can say it's and chips, a photo of guacamole, a type of food. Airplane, it shows a photo of airplane. So you can see that you feed it an image, you get text out. It's kind of like the reverse, right, of Stable Diffusion. Here's like the architecture of this model. You'll see some like similar things showing up again, like a text encoder, image encoder. Then there's like a classifier in there that generates the text of what the image is, and a text encoder, and finally like the text that comes out. The architecture is less important for these models, honestly. I think like what I want you guys to keep in mind is just like the intuition of essentially what's happening, because we only have a few minutes to really cover each model. One other thing about Clip is that it's a zero-shot classifier. So that means that you don't have to actually train it. It's like zero shots are used to build models for classes that have not been labeled in training yet. So it's like a new image that gets fed in, and it can kind of attempt at giving you an estimate of what that is. All right. Warnings with Clip. Here's the stuff that it struggles with. Poor generalization to images not covered in its pre-training internet data set. Counting number of objects it struggles with. It's not good with very fine-grained classification, like the difference between car models or variants of aircrafts or flower species. It's kind of like a general text generator based on images. It's not great with complex tasks like depth in a photo. All right. So the exact model you guys are going to use today is called Clip Interrogator. Here's a link to it on GitHub. And it combines OpenAI's Clip that I just discussed with Salesforce Blip to create the text prompts from the images. Here's just like an example of this. Here's like an image that got fed in. Here's a Clip model. And you can see this like really long prompt it gave based to describe that image. All right, so that's Clip Interrogator or Clip, right? Like almost like, here's like the other model from Salesforce and a little bit of information about it. So Clip Interrogator is like a combination of these two. All right, so that's kind of like a reversed image stable diffusion, right? All right, Llama 2. There's a bunch of Llama models, 7 billion, 13 billion parameters, and 70 billion parameters. They were all trained on about 2 trillion tokens. The context length is 4,000 tokens. And these were the fine-tuned data sets that were used for building the chat version of these models. So this is a really new model as well, released about a month or two ago. Actually, this is Code Llama, sorry. This is a slightly different variant. So Code Llama it comes in 7, 13, and 34 billion versus the like text chat models are 7, 13, and 70 billion. The Code Llama was trained on 500 billions. It supports these languages. The 2 smaller models also have like a code completion capability. And there is also a specific Python model and a instruct fine-tuned model. We're not going to use these Code Llama models today, by the way. We'll use one of the chat models instead in the lab. So what are like the most important things you might want to know about this model? So this generation of chat models like Llama 2 is trained by generating during training, it's asked to try to generate the next word in a sequence given the preceding words. So this type of model is considered auto-regressive and a decoder-only LLM. What does that mean? Auto-regressive essentially means the model depends on its own past behavior. So you can, so it essentially generates 1 token at a time, and then it uses all of the previous output, including your prompt or prompts and text that it generated, to then generate the very next token. So that's what autoregressive means. What does decoder only means? It only has the decoder part of the traditional transformer sequence-to-sequence model. The encoder is emitted, and the model starts directly with the decoder. Remember, the encoder is like what essentially like takes text and has to convert it into like a matrix representation. Well, with these chat models, you give the very first starting point, right? Like you give it a prompt, and that gets fed in to start this process. So you don't need the encoder. It was trained on, this version of Llama 2 was trained on 40% more tokens than the previous generation Llama 1, and it has a 4,000 context length. I'm going to talk a bit about what that means in a second. It was trained on NVIDIA A100s for 180 hours for the 7 billion or 1.7 million hours for the 70 billion. This is how much carbon emission that would be. Here's some of the internal architecture details. All right, so I want to talk a bit about this context length thing. I think it's important to understand. 4,000 tokens is how long the context length is. This determines how much text the model can see at any given moment. It includes your prompt that you kicked off the process with, the LLM's response, and all future prompt response pairs. If the conversation goes beyond this length, either the text needs to be truncated or shortened so it fits in that size of the context length. And obviously, if the text gets truncated, then any reference to those parts won't be understood by the model anymore. And another really important thing to understand about this is when you start your conversation with the LLM, it'll be much faster because the context is pretty small at that point. And then as you have more back and forth with it, inference will actually take longer and longer. So like the 10th response it generates in a conversation will take much longer than the first response it generates, because in the first response, it might just be at like about 100 tokens. and then you talk to it, then it talks to you, then you talk to it, and you're like building up the context until you get to like 4,000, and then that's kind of like game over. The context has filled up. This context length being small is probably one of the biggest problems to resolve in the current generation of LLMs. And there's a lot of work happening in this space. Like there's some models with like 40, 50,000 context, but even then there's a lot of study that's coming out that like it's still kind of forgetting what you said in the very beginning of the context. All right, so let's kind of talk about what happens behind the scenes when you use an LLM. Tokenization is a process that converts words to numbers. The dictionary for Llama 2 is about 32,000 tokens. That's like the vocabulary. It's essentially the process of converting words into numbers, right? So one token is about 4 characters of text. OpenAI has a really nice website that is called a tokenizer. You can just paste some text in there and it tells you how many tokens and characters it is. You can see how it breaks it up, right? Like artificial, that's 2 tokens. Intelligence, that entire thing is 1 token, including the space in the front. And then it added a space there, AI, so you can kind of see how the tokens are breaking up. GPT-4, like the $20 paid version of ChatGPT, can process 32,000 tokens in its context length, I think. I think that's actually how large its context length is. It's almost like a book. Llama 2 is like 2 long newspaper articles. It's 4,000 tokens. And there's like a bunch of tokenizing algorithms. There's like TickToken and GPT encoder and a few others. But that's the first process. You got to get tokens out of your text. So here you can see at the bottom it converting into numbers. All right, after you do that, then the tokens are assigned to the equivalent of definitions by placing them into a meaning space where the words that have similar meanings are located in nearby areas. So you can see like these words kind of are related, these words are related, those and those, right? So that's like the intuition of what's happening next, this embedding process. And then the LLM deploys its attention network. Remember, this was based on the transformer like attention architecture. And what this does is it makes connections between different parts of the prompt. So someone reading our prompt here, which is the promise of large language models is that they, when you read that, you would know as a human how English grammar works. Like it's obvious to a human which words relate to each other. Like it is the model that is large, for example, here. So that is essentially what this process is trying to figure out. Like models relates to the word day, that's like 30%. Models relates to large, like 15%. And it does this for every single word. For every single word, it essentially tries to figure out like what surrounding words does this word actually relate to. Like here, day refers to models with 75% probability. So this is just like the LLM essentially trying to understand what that language is saying. And then it has to create a response. So once the prompt has been processed and like tokenized and the embedding and an attention network has been run, then the LLM initiates a response. At this point, for each of the tokens in the model's vocabulary, the attention network has produced a probability of that token being the most appropriate one to use next in the sentence it is generating. And the token with the highest probability is the one that it sends forth. So here, if you feed a completion type of LLM, like a base Llama 2 model, this initial part of the sentence, then it will, like with a 62% probability, decide to put the word can next. And then it just kind of keeps continuing that process to generate all of the next words. This is not like there's some creativity involved here. As you can see, like there's many different probabilities. You can actually, one of the parameters in Llama 2 is like a creativity parameter where you can like dial out its creativity so that it'll like not try to pick the most probable word, but kind of jump down to the third, fourth, or fifth word. You can also control like how many words should it even consider, like the top 5 words or the top 3, and don't even go below anything like the top 5, because then you're getting into like poetry at some point. So we are going to use a fine-tuned chat version of Llama 2. The way you interact with those chat models is like the way you already realize how to interact with a chatbot. But if you work with one of those base models, then I want you to remember this word schizophrenic. Adrian Gomez right here is one of the authors of the famous attention paper from 2017 that like kicked off all of the LLM stuff happening right now. And when he was asked like, hey, you know, what's the deal with like these base models? Like, do you have to fine tune it? One thing he said is like, look, if you don't fine tune a model, it kind of behaves schizophrenic. It's like all over the place. It's hard to get it to do what you want it to do. Like you try to give it instructions and it just breaks in unpredictable ways. So keep that in mind. Like if you're using a base LLM, you can't have a chat conversation with it. What you instead do is like you give it the beginning of a sentence, submit that, and it will just try to complete that, right? That's all it's going to do. I mean, if you end your sentence with a question mark, then yes, it'll like consider actually responding to that because it realizes that's a question, and then for the next thing, there should probably be like an answer to that question. But you can't really have a chat conversation with the base model. Cool. All right. This is how ChatGPT was built. There's essentially like a pre-training process. There is a fine-tuning process with less data, and then a human reinforcement learning process. Same thing with Llama 2. You'll see always that trifecta of pre-training, fine-tuning, and human reinforcement learning. All right, let's skip through a little bit of this. These are some famous fine-tuning data sets. One thing I want to point out is like since chat versions of Llama 2 were released, you don't need to fine-tune to get a base model to behave as a chatbot anymore. So a lot of these data sets were created in the past year to do that process of fine-tuning a base model so it's not schizophrenic and instead can behave in a chat-like way. But with Meta doing that for us, like we kind of don't need to do that anymore. There's a few other concepts here, like prompt engineering is essentially iteratively trying out a bunch of prompts until you get it to do what you want it to do. Which RAG is this concept of taking a bunch of like PDFs, converting them into vectors, and storing that in a vector database. And then every time you want to query those PDFs, the chatbot will go to the vector database, get the facts from the PDFs that are embedded in the vector database, bring that into the context length, and use that to answer your question. So it's like using a side database to get your answer. We'll kind of skip this hallucination slide. You can skim through it if you'd like. And this is actually something interesting, a concept called emergence. Has anyone heard of this? Emergence in LLMs. One interesting thing that's like being discovered is like as you get larger and larger models, they seem to be doing things just a little bit like a phase step in physics. Like suddenly it couldn't do it, and then at a certain size it can suddenly do it. Here are some examples of things that are considered emergent behaviors. An OpenAI researcher had 137 things that he wrote out as emergent behaviors in LLMs. All of the like fear around generative AI and like artificial intelligence doomsday coming around has to do with this idea of emergence. Like if you suddenly get to a really large model, it might bring forth harmful or useful behaviors that are like lying dormant in the model and only gets unleashed at a certain scale. All right, there's a couple more things I want to really quickly cover before you guys do the labs. Control net is a really interesting concept that we will look at in Lab 2 today. So here are a couple of links you can play around with on your own time. These are both links that engineers at OctoML, including Thierry, who's going to be the next presenter, created. QR Chef, what you do is you upload a image to it, and then actually you give it a URL of like something like a QR URL you want to embed, and it'll give you an image back that is actually a QR code. The way that works is actually interesting. Like for these QR codes, I guess you only need like 85% of the image to be correct, and then it still works. So, so this thing can be a little bit lossy and not do it perfectly, but the code, the links still works. This is another control net demo where you send it a logo, and then it will kind of like embed that logo into an image of some food. Here's like a pizza and with the OctoML logo. So essentially what this thing does is it lets you control better how the Stable Diffusion network creates the image. For example, with ControlNet, you can send it edges called like canny edges here, which are like intensity changes at the edges. And then by default, a ControlNet can create a image out of that edge space. You can see the default images like here that it can create. Here's like a human pose, and then Stable Diffusion can create an image of a person in that pose. You can't do this with a prompt. That's why we're discussing this, and you'll see this as a demo in Lab 2. No matter how much you try, you're not going to prompt Stable Diffusion to probably get a guy standing just like that. So that is something that you'd have to use ControlNet to get that kind of granular control. Again, a very, very new model, like February 23 is just when the paper was published by Stanford. So this is the default here. With what we're doing is we're using the ControlNet like edge or pose and feeding in a prompt at the exact same time to now have the prompt give some information to ControlNet, and ControlNet's like edges also give some information for how the final image should look. All right? So you're just like essentially controlling a little bit with more granular detail how Stable Diffusion will create the image. All right. There is a paper here that you can go refer to if you want to learn more about the details here. But essentially in ControlNet, like the Stable Diffusion model weights are frozen, and then there are some trainable weights that is like your condition that are embedded on top of it. This is the architecture, and if you're interested in this. Okay, the last model I wanted to cover is called Face Swap. This is another more advanced model that we're not going to get to until Lab 2. It was created by a handful of people from an organization called Inside Face. These are the exact libraries we're going to use with Face Swap. And it actually, like this thing is like a bunch of different models. You can see there's a face detection, face alignment, face recognition. And at the end of the day, it lets you swap out faces. Again, something you can't do like in Stable Diffusion, right? Like if you make an image like this in ControlNet, what if you want to put like your face in there? You can't do that with just Stable Diffusion or ControlNet. So you have to bring in a face swap type of model to do that last step. All right. I think that is it. Any questions about what we covered? I know that was a lot. And remember, all you really need to get here is like intuition of these models, right? Anything? Yes?
Where do we get these slides?
It's a great question. There is a link here at the very top. tinyurl.com, DockerCon GenAI, and then there's a link. There's a bunch of links here. Here's the slides link. There's a labs link, and that'll get you to this page. So once again, just remember DockerCon GenAI and tinyurl.com. All right. So next, I'm going to hand it off to Thierry in just a second. And I will put a link to the pre-class survey PDF in the notes doc as well. This is essentially what you guys are going to do. Before I go, please remember you have to really run this Docker build command before you go to break. That thing's going to take almost exactly 20 minutes. So kick that off, make sure your laptop is plugged in, and then take off for break. We're going to resume at 9:15. I'm going to hand it off to Thierry. And Thierry, you want to cover the rest?
Yeah.
Okay, cool.
Okay, everyone can hear me? Great. Can people hear me in the back? Okay, awesome. Well, let's give a round of applause to Samir, who just gave us a very comprehensive crash course on a lot of innovations over the last year or so. It's mind-boggling how quickly this field is constantly reinventing itself and revolutionizing the state of the art in AI. And so let's see. Okay. As Samir pointed out, there's a class notes document here that we dropped in Discord. If you sign up for this workshop, you should have received a link to that Discord channel. If you're not in there by now, please do join this OctoAI server. There is a DockerCon 23 channel. I just dropped the class notes link in there. Once you're in that document, you will be able to access the lab instructions. And this is what we're going to do after the break. So once you're in the lab instructions, we're going to click here on the link, and you should be greeted with this page here that gives you an overview of the lab you're going to go through. And just to give you a bit of a flavor of what kinds of really interesting things we're going to be doing with generative AI, here's a preview of how you can transform the Moby Docker logo into a very realistic picture of a whale with a container on its back, right? So that's the kind of magic you're going to be able to do. You can even send it to space. We're going to do a lot of very interesting things. Samir, just a moment ago, talked about control nets. You're going to be able to apply this to more or less match the layout and the composition of that logo onto a very realistic image. And we're going to apply this to pictures of people as well. So here's the Mona Lisa in space. These are the kind of things we're going to be able to do today. So I hope you're all excited. In order to get started, though, as my colleague Samir pointed out, you will have to go through the prerequisites here. So on this page, access the prerequisite link on the side, and it will give you a series of things to do. So by now, you've already joined Discord, I believe. And actually, we're going to make the DockerCon 23 bots channel public. Then, if you haven't done this already, do get a Docker Hub account, because we're going to be creating container images, and we're going to be uploading them on Docker Hub so that we can host them on an OctoAI endpoint. This is how we're going to serve inferences. And this is how, if you're a developer and you want to build a GenAI powered application, by using these OctoAI endpoints, you can actually scale your deployment from one node to potentially dozens, if not hundreds of replicas in order to run generative AI powered applications at scale. So do sign up for Docker Hub. Do sign up for an OctoAI account, because we're going to need this to run our inference endpoints in the cloud. And then the last piece, which is very important before you head out for break, is to get set up with an AWS dev instance. So we've created EC2 instances for every single one of you. There should be enough for everyone. You're going to need those, because this is where we're going to build your containers. The reason why we can't do this on your laptop is because your laptop doesn't have a multi-$1,000 GPU on it to run these very compute-intensive models. So we're going to need to do this in the cloud. We're going to need a GPU. Yeah, 1 second. All right, is the audio better? Okay, I'm not getting echo, so this is wonderful. Thank you. So yes, do grab an AWS EC2 dev instance. The way you're going to do this is that there's a spreadsheet here. You're going to click on it. Once you're in that spreadsheet, you can claim your AWS EC2 instance. So do grab an address here, put your name in, and you're going to be able to download a .pem file this is what's going to allow you to securely access the endpoint. And essentially, we've made these available to you for the day. These are going to be brought down, so you're not going to be able to access it after today, but at least it will allow you to build these containers in the cloud. Also, that allows us to get around network limitations because we are going to be moving a lot of data. These containers are not your grandpa's containers. They are several tens of gigabytes large. So we can use all the help we get by running the build and the upload to Docker Hub from an EC2 instance. So do go ahead and claim your dev instance. And once that's done, as Samir pointed out, I'm going to ask you one last thing, which is to, once you've completed all the prerequisites here, which includes SSHing into your instance, so just making sure that with this .pem file that you're going to be able to access this instance with the Ubuntu username. And there's a extra flag that we've added here to enable port forwarding that you're going to need to add. So you're going to enter a version of this command here that is personalized to your instance. Make sure to add the port forwarding here from the dev instance port 8888 to your own laptop's port 8888. And what this will allow us to do is then run Jupyter Notebooks on your laptop. All right, so there's a few steps here that we need to go through, but once you've SSHed into the instance, the very last thing I'll ask you to do before heading for break is just to build your very first model container. So in lab 1, before you go, just type this command in this directory here. So the very first step of section 1, which is to go in that directory once you SSH in, and to type this docker build command. Just make sure it's running. And as Samir said, it will take some time because it's pulling a base image with a lot of dependencies. It's setting up the different apt packages. It's installing the different pip packages listed in the requirements file. I'm going to go over this in more detail, but please do run this. So we have 5 more minutes before the break starts and then 15 minutes of break. So you have at most 20 minutes to just go through these steps. Do let us know if you're running into issues. But I'm hoping that you all have time to go for a break to maybe grab some food, coffee, go to the bathroom and come back. So we'll just have to make sure enough people are back in order to resume lab 1. So please go ahead and do flag any problems on Discord if you run into any. All right, thanks everyone. All right, now everyone can see my slide. Just wanted to recap on the schedule today, which has been modified from what you can see on the website. So there's going to be a lab session starting now that's going to extend until 10:30, so for the next hour and 15 minutes. So that should give us enough time to go through this very first component that I'm going to walk you through. We're going to have a break, and after that, my colleague Luis Vega is going to present lab 2, which is going to last an hour. We're going to build a slightly more advanced generative AI-powered Discord bot. And then we're going to use the last 15 minutes to have some closing thoughts, look at each other's creations. Hopefully a handful of you, maybe even better, most of you will have gone through those labs in order to have an actual bot that we can play around with, interact with, generate some really fun and creative images with on Discord. And we'll start with some Q&A if we have some time. So that's the plan for the remaining 3 hours or so. I wanted to introduce myself. My name is Thierry Moreau. I'm a co-founder at OctoML. Also, today I'm wearing the DevRel hat. And my colleague Luis Vega here, who's a very talented ML engineer at OctoML, will help me go through this really exciting, interactive and engaging generative AI-based lab. So I'm hoping that you're all very excited about this. I wanted to give a couple introductory slides before we get our hands dirty on this OctoShop idea, which is to transform photos with just the power of words. And this really started when I wanted to build a photography app using generative AI that would travel through time and space. You could transport the subject to a different place. You could transform them to a different era even. What do I mean by that? So, for instance, let's take the Mona Lisa. What if we could take that very famous woman who's been painted by Leonardo da Vinci and set her in Japan in the 80s, for instance? And so the idea was to create this pipeline using a bunch of generative AI models, the same ones that Samir introduced us to, which I call OctoShop, as a nod to a software program that starts with photo and ends with shop. So you would feed an image to it, and you would also set a prompt, for instance, asking the OctoShop to set the photo in 80s Tokyo. And sure enough, it would place the subject into this setting of 1980s Japan. And it's not just about taking that foreground and placing it into a new photo with a different background. You're actually transforming the entire style of the person. The hairdo, the fashion, the jacket, the clothing is all reminiscent of a time and place. So this is part of the magic of OctoShop, and this is something that I'm going to teach you how to build today. By the end of this session, you will have the tools to build this on your own, which I think is really exciting. It doesn't just work on famous paintings, it can also work on individuals. So here's a photo of myself hanging out at Toronto Pearson Airport. I live in Toronto. And what if you could set the photo in a Barbie world, right? So it doesn't have to be time and place. It could be in your favorite movie, right? And sure enough, the result is me hanging out at an airport dressed up as a pilot Ken for some reason. But it does stick to the prompts, which is great. So looking underneath the hood, let's see what powers OctoShop at a glance, because we're going to be essentially building this ourselves today. To build this baseline generative AI, we're going to rely on Clip Interrogator, which Shamir already talked about, which takes an image and produces text, a textual description to be more specific of that image. Then we're going to use Llama 2. And if some of you are not familiar with Llama 2, I'm sure you used ChatGPT in the past. Llama 2 is an open source model. And what it allows you to do is provide text. For instance, ask it to set this close-up of a painting of a woman in, say, 70s Hong Kong. And that will produce a detailed story of a scene. And it's going to introduce concepts and elements like neon lights, Hong Kong's bustling streets. So I didn't provide this to the OctoShop pipeline, right? I just told it a place and time, but it will fill in the details and the contextual elements to really transport you into this scene of 70s Hong Kong. And sure enough, once you feed that into a text-to-image model like Stable Diffusion XL, you will get a photo of the Mona Lisa with, the neon lights in the background, the busy, bustling streets that really sets you at this time and place. And so all these models can be run on OctoAI compute services. This is what we're going to use to build this original pipeline. This is like going from 0 to 1, right? You build the original pipeline, you build your prototype, your demo. But what OctoAI allows you to do is go from 1 to 100. What happens when you need to scale this and serve these models at production scale in a production web app or any kind of front end? In this case, we're actually going to be deploying a Discord bot. So for today, we're going to do the 0 to 1 step, but I'm going to show you the tools to go from 1 to 100. And with OctoAI Compute Services, it's actually fairly simple and straightforward to do this. Some of our customers in the generative AI space serve upwards of hundreds of thousands of users. So this is something that can scale. We're just teaching you the basic tools to build a demo, but know that from what you're going to learn today, you're going to be able to scale this to production scale using these tools. So these are going to be very useful skills that you can take home today. In Lab 1, as I showed you, we're going to learn how to use Clip Interrogator, Llama 2, and SDXL to take the Mobi logo and set it in very interesting settings. For instance, a hyper-realistic image of Mobi. We're going to send Mobi to space. We're going to learn how to do all of this. My colleague here, Luis Vega, has also put together this really great gallery of SDXL styles. So these are all the different kind of styles that you can use in Stable Diffusion. And that's going to allow us to really create very unique feels and consistent looks for the images that we generate using Octoshop. So a very useful tool in our generative AI tool set. In lab 2 that Luis is going to present, we're going to learn how to leverage the control net. So Samir touched on this a little bit, but you can see we have much better consistency between the input and output photo here. You can almost superimpose these two photos and see that in the new GenAI-based image, we can actually trace the contour of the original Mobi logo, which is the goal of control nets. And we're going to learn how to achieve face consistency between input and output images, as exemplified on this Mona Lisa in space. Right? So these are tools a bit more advanced that we're going to learn in lab 2 to build this complete pipeline. All right, so let's get started on the lab here. Actually, last note. For those of you who go through the lab by the end of the session, and really we'll get there by lab 1, which is gonna be what we're gonna be doing over the next hour or so. By the end of lab 1, you should have a Discord bot up and running that allows us to upload images and do this processing automatically. All right, everyone's gonna have their own unique bot. Here I chose a a space theme, but you can go ahead and set the prompt to anything you want. You can hard code that. And so for instance, if you want the bot to be the one that places pictures in a Barbie world, you can make that your own bot. Everyone's gonna try to have a different unique bot. And that's gonna keep this lab really interesting and engaging. All right, so by now, you probably already have accessed this URL. For some of you who are joining just now, please do access the resources through Discord. This is where we're going to start and follow the instructions to get started on lab 1. So let's jump right ahead onto this link. Again, by now, you should have completed the prerequisites, which are listed in this page. For those of you who haven't yet, please, don't let this deter you from going through the prerequisites. You might not be able to follow along in real time, but please do go at your own pace. And keep in mind that everyone's going to be able to access their own EC2 instance that they can claim from the spreadsheet that is linked here in the prerequisite page. So everyone's going to be set up with an AWS EC2 instance. And the reason being, again, that you need a pretty powerful GPU for development here, for building and testing your Docker container that contains all of the model goodness that allows us to serve it at scale. And in order to do so, you need a very good GPU, which we can access in the cloud. All right, so I'm going to go ahead and type in this command here in my terminal to access my very own EC2 instance, which I've claimed here, right? I'm the instructor. I have this EC2 address, and I've already typed up a command that will allow me to access this instance. All right, so I'm SSH'd in. And the first thing that I asked you to do before the break, if you recall, was to start building a Docker image of SDXL. So I'm going to go over to instruction of lab 1. The baseline Octoshop pipeline. And so this assumes you've already gone through the prerequisites. We're going to go to this directory. So when you SSH into your instance, we've already pre-cloned the GitHub repo, so you don't have to clone it yourself. I'm going to go to this directory. And if I do an ls here, you'll see that there are several files. If you've used Docker before, these are going to be familiar to you. There's a Docker file. There's a handful of Python files and a requirement.txt file. So I'm already set up with VS Code. Who here uses VS Code, by the way? Okay, a lot of people are familiar with it. So, for those of you who are proficient with VS Code, you can also set up, in your SSH settings, you can add the EC2 instance, point to the identity file, put in your host name. User account is Ubuntu here. That's an important detail some people miss from the instructions, so I'll just remind people here. But given that a lot of people are already using VS Code here, I can recommend people very enthusiastically to use that but for those who are old school and like to use Terminal and Vim or Emacs, please go ahead and use that. I'm going to go and open up some of the files here that we've used to build the Docker container. So you're going to see a Docker file, and this is pretty standard, right? We have a base image. We're using an NVIDIA CUDA one that has all of the NVIDIA software stack pre-installed on it. This is very important for deep learning because we're relying on GPUs a lot. We're going to install some apt packages, right? These are the dependencies that we need to be able to run our models. And also the requirements.txt file that contains a handful of pip packages, some of which you might have never seen, or maybe you're familiar with them, depending on how much exposure you have to deep learning. But here we're using packages like Torch, transformers, OpenCV, etc., diffusers. So these libraries are the ones that we're going to rely upon to run our Stable Diffusion XL model. All right. Specifically diffusers here, which is a library by Hugging Face in order to run Stable Diffusion models. But there's a lot of other libraries out there. We're just using one that's easy to get started with. If you go into server.py, you'll see that this is essentially a scaffold to run an inference server. So this relies on the SANIC library, and we're going to define essentially the scaffolding or a skeleton to run an inference server. So there's going to be a couple endpoints, a health check, which is an endpoint that we use to check whether or not this inference server is up and ready to service inference requests. And there is a predict endpoint that allows us to send inference requests to that inference server. You don't have to change any lines here. This is essentially just scaffolding. The model.py is what contains, all of the generative AI goodness. And by the way, is this large enough? Should I make this a little bit larger? Maybe this is better. So the model.py file is where we're going to define the model class. And it's going to have a couple methods, including init, which is performing the initialization of the SDXL pipeline. You're going to recognize some of the components of that Stable Diffusion model that Samir alluded to, like the VAE or autoencoder. We're going to initialize the Stable Diffusion pipeline from a pre-trained model, just a base SDXL model. And then there's several optimizations here that we just added in order to make sure we're running this model in the best way possible. You don't have to touch that. But essentially, these are memory optimizations or making sure that we're using the GPU to its fullest extent. And once all of this runs, it will print SDXL pipeline has been initialized, right? So this is what happens when you start running the container. It will initialize the SDXL model. And the predict method is really where all of the code that runs the SDXL inference is going to be defined. So it takes in an input dictionary and produces an output dictionary. We can parameterize and customize this input dictionary, but for this very first lab, we're going to leave this code as is. So it's going to contain a prompt and negative prompt, which Samir alluded to in his Stable Diffusion crash course, as well as guidance scale, which is one of the Stable Diffusion parameters. Number of inference steps, width, height, and the seed in order to control the outcome so that it's not random every time you invoke the model. And that's going to produce a base64 encoded image as a string. All right, so we're taking all these input parameters, we're just printing them, and then we're just passing them into the SDXL pipeline. We're just calling this, and then this returns images, and we're just returning the first image because we're only generating one image at a time inside of this completion dictionary, and just returning this. That's all there is really to this model container, these handful of files. What I'm going to do here, and I've already run this ahead of time, but I assume you all started before we did the break, so by now, hopefully, your build is done. But I'm going to type in this docker build command, and that should build the model, and we should have a model built by now if I do docker image ls. If you're not done, fear not. You can go at your own pace because I'm going to step through the lab. It's going to be hard for me to make sure everyone's caught up. So this is mainly for the recording so that people async and follow along, but go at your own pace. So at this point, I've already built an image, and we can see that at the top, in the list of in the list of Docker images, there's an SDXL image that I've built. What I'm going to do is now I'm going to run in section 2, I'm going to take this command and type docker run, which is going to run a container based on that image I just built. I already have a container running, so I'm going to do docker stop SDXL. Okay, I already had a container running, so this is not something that you need to do. This will just take a few seconds. Just quick show of hand here. Who has completed their container build here? Okay, so that's pretty good. I count about probably over half to 3/4 of the room. For those who are still running their container build, I'm just going to go ahead and step through the lab, but you will have some time after I'm done talking to go at your own pace. All right, so I'm going to run this SDXL container out of the SDXL image. And so that's going to launch the container, because again, if we go to the Docker file, what you'll see at the bottom of the Docker file is that when we finish adding all of the different files and importing all of the, installing all the different dependencies, we execute this command here, which is to run the server. And then the server launches and initializes the model, et cetera. So if I do docker logs SDXL, I should see that, all right, this NVIDIA-based image has, the CUDA software stack pre-installed, and it is printing here in the logs that it is initializing the SDXL pipeline, which is something that we're printing here at the beginning of the initialization method. So it shows that things are getting up and started. All right, so this will take probably a couple minutes because initialization is not something that is typically really fast. It takes a lot to prepare the pipeline. So while this is initializing, I am going to start a Jupyter notebook. So I'm just going to start another terminal session here. I'm going to SSH into the same machine, but when you're about to start your Jupyter notebook, it's very important that you set up port forwarding here so we can run the notebook from your laptop. This port forwarding command is described in the prereqs page at the bottom. If you're having issues, just ask on Discord. People will point you to it. But here I'm setting up port forwarding, which will allow me to launch my Jupyter notebook. All right. So remember, we're still launching the container. If I type docker logs again, I can see, okay, there's been some initialization code here. We can see it's loading the pipeline components. It's reached 100%, and now it's printing SDXL pipeline has been initialized. So now on that EC2 instance, I have my Docker container up and running. It's listening at localhost port 8080 for incoming inference requests. So this is running locally to the developer instance, which will allow us to essentially test this container locally to the EC2 machine. I'm going to launch my notebook now with the command that's described in section 3. So I'm going to go to this directory, DockerCon Lab 1, and I'm going to go ahead and start the notebook. And while that is up and running, I'm just going to grab some water. Okay, so at this point, we're launching the Jupyter Notebook server. We added this no browser flag because we're not going to be accessing the server from within the AWS instance. Instead, we're just going to run a server. It's going to be listening on this port for incoming request, which is the port that we're forwarding to our laptop. So if we've done the setup correctly, at the bottom of the Jupyter Notebook logs upon startup, there's a link here. You can grab either one of these two, and if you paste it in your browser, you should have the Jupyter Notebook up and running. All right, so we can see that there's a Lab 1 IPython notebook. this is what I'm going to start up. So I'm going to go ahead and launch this. Who here has been able to successfully launch the Jupyter Notebook server? Okay, there's a handful of hands raised, so I think the pace is good. For the rest of you, go at your own time. Again, there's going to be time for you to catch up at the end. All right, so let's take a look at this notebook here. We're going to stay on the notebook for a bit now. So we're going to build this baseline Octoshop pipeline, and we're going to interact with it through the comfort of our notebook. So I'm going to go ahead and import these dependencies, these Python packages. There's a library called OctoAI, which contains the OctoAI SDK for Python. We're going to use this to communicate to our locally running container, as well as the remotely running container hosted on OctoAI. Essentially, it's a helper. It contains helper functions in order to send HTTP GET and POST requests to a remote server. So it's fairly straightforward. What you just need to do here is initialize the client with this line of code. Ignore the warning, because usually you would pass in a token for authenticated access, but all the endpoints we're going to launch are enabled for public access. So we're going to go ahead and test our SDXL container locally. I have a list of parameters here as a reminder of the SDXL inputs that you need to pass in order to submit an inference request. So this is described in this payload dictionary. What we're going to do here is that we're going to generate a photo of an octopus playing chess. And we also provide some negative prompts here. Learning how to engineer prompts is a bit of a dark art, but over time you get the hang of it. These strings, for instance, are ones that you find a lot in SDXL inference requests to get realistic images. So you're telling it, I don't want a blurry photo, I don't want distortion in my image, I don't want something that looks low res or has bad quality, right? These are all more or less negative qualifiers. And I'm just going to set these other parameters. Number of inference steps. 20 is a good number. You can go for more steps, and that will generate more refined images, but that's also going to mean that it's going to take longer. So remember, we have the container running locally, and it should be listening to incoming requests at this address. So what we're going to do is that we're going to send this payload to this URL, and that should get us an image. So let's go ahead and get started here. I'm going to run this cell, and within about, let's say, 8 or 9 seconds, I should have an image back. So let's see what happens when I run this on my container. And I can also print the logs here. If I type docker logs SDXL, I can see that I got a new request here, right? So I'm serving this inference request, and sure enough, it is that photo of an octopus playing chess. So it shows that I'm actually running the server, it's listening for requests, and look at that. We have a beautiful photo of an octopus playing chess, right? Wonderful. So this is running locally. Now we want to take this container image and upload it to Docker Hub. So I invite you all to do this. You may or may not have to start a new SSH session, but I'm just going to go ahead and go to DockerCon OctoAI Lab 1 SDXL in my terminal from where I ran the container. And from this directory, I'm going to go ahead and tag the latest SDXL image and point to the Docker Hub username, which you by now should have created, and the repository that I invite you to create in Docker Hub. And this is where we're going to upload our SDXL image. And we're going to version it to 0.1.0. So if I go to my Docker Hub here, we've already provided the links. I've already created a repository, which I named DockerCon SDXL. My username here is tmoro89octo. And I already uploaded the image, but originally you shouldn't have any images here. If you just take your username and the repository name, you can go ahead and Docker tag your image, so SDXL. Clear. All right. Docker tag SDXL latest, and then paste in. Oh, something weird happened. Clear. Docker tag SDXL latest. Moreau 89 Octo, DockerCon, SDXL, and then version 0.1.0. All right, so I've tagged it. This should run instantly, and then Docker push, and then use the tag that I just created to push it to the repo. All right, so because I've already uploaded it before, it runs instantly because everything here is cached. But for you, it's going to take a few minutes, depending on the speed of your network on the EC2 instance. So at this point, if you're running this, this is going to run in the background, and we're going to go ahead and start playing around with the IPython notebook. All right, so while this image is uploading, and by the way, if you don't have patience, I've provided you with my own image that you can use here at the bottom of the cell. So if you don't have the patience to wait for this to upload, we're all going to have the same container image anyways at this stage. Feel free to use mine. That will save you about 10 minutes. What we're going to do next here, and we can go ahead and grab this image link, SDXL. What we're going to do ahead in the next step is go to OctoAI. So by now you all have created OctoAI accounts. This is what we're going to use to serve our model container. So if I go to this link that I've provided to you, octoai.cloud/endpoints, you click on this link and you can create a custom endpoint. Once you click on create a custom endpoint, you can paste in the container image. You can use mine or you can use your own if you want to wait for your image to upload to Docker Hub. But here I'm just going to use mine. And I'm going to call it, say, DockerCon SDXL. And I've already provided information here on how to configure it, but I'm going to go ahead and do it live in front of you. So we're going to leave container port as is, as well as registry credential. I'm going to provide a health check path by just typing in health check. I'm going to enable public access. This is an important point, so we can access our endpoint without having to authenticate. Another important detail is to set the hardware tier to medium, because small is not powerful enough for our SDXL model, unfortunately. And large, I don't recommend you using it because we don't have the quota to have every attendee launching large instances. So please do only run medium instances today. And then in terms of auto-scaling, I'm going to set the min and max replicas to 1. So the magic here is that if you want to run this in a production setting, you can take advantage of auto-scaling. And you can set min and max to whatever number you want. It could be 10 or 100. By default, all accounts are restricted to a max of 10. But let's say if I set max replicas to 10, that means if I'm getting more and more requests coming in and hitting my endpoint, it will launch additional replicas to do load balancing across more GPUs. So you can enforce SLAs to, say, the client hitting your inference server to make sure that you can, produce inferences as a given throughput or meet some P95 inference latency constraints. So I'm going to go ahead and set min and max replicas to 1 and then hit create. And that's going to launch my inference endpoint based on that Moreau 89 Octo DockerCon SDXL image. All right, so you can use this one that I'm giving to you, or you can go ahead and wait for your container image to upload to Docker Hub and then use that Docker image tag in your OctoAI endpoint deployment. So that's going to take a little bit of time because now this OctoAI inference endpoint is going to be pulling that image we uploaded to Docker Hub onto its own machine. or its own replica. So if you click on View Event History at this stage, some of you might be at this stage, so if you've launched it based on that image that I've provided you with, if you go to View Event History, there's no events yet, so we're just starting up. We're going to monitor this endpoint maybe in a couple minutes, because sometimes it will take a few seconds or a minute or two just to start up, and I think everyone here trying out this lab might be hitting our service at the same time. So I'm just going to go ahead and go back to the lab 1. So at this point, I've gone through step B and step C, and this is going to take some time. So while we wait, you can go ahead and jump to step E. As long as you have your container running locally in Docker Engine on your AWS EC2 instance, we can play around with Stable Diffusion. So what I'd like to introduce you in this section E is the concept of styles. And I'm going to go ahead and access the website that my colleague Luis built. And you can see that we've been able to show and emulate all these different SDXL styles on the same prompt. So, one of the styles that I particularly love is this claycraft style. As you can see, there's a really fun and playful image of Moby in claycraft style. And this is something that you can access and emulate in SDXL using the right prompt engineering. There's about 100 of these different styles that you can look at. For instance, origami, I find particularly fascinating here. It looks like Moby was built out of just origami paper, right? There's pixel art, all kinds of other styles. Gourmet food photography. Here, it looks like Moby has been made out of this very appetizing Jell-O dessert. So, and also, real estate ads, retail ads. Really, there's a very long list. Also, different kinds of art styles, so pop art, psychedelic. And the list goes on and on and on. Also, your favorite retro arcade style, right? Really reminiscent of playing arcade video games. So I invite you to play around with this, and you can play with it now as soon as you have the Docker container running locally in an EC2 instance, because remember, we're just hitting localhost here. So I've selected a style from this page. If you access these JSON styles, you'll see that there's essentially just a dictionary of a list of those styles here. Each style is these few lines, this dictionary containing name prompt and negative prompt. So whatever style here inspires you, for instance, one that I liked was the retro arcade. If you search for retro arcade in one of these files, arcade, there we go. So you can copy this dictionary and just paste it right here in this SDXL style definition. So what happens when I run this cell is that this is going to apply the Stable Diffusion style of retro arcade onto my photo of an octopus playing chess prompt. So let's see what happens here when I run this, this cell, and within a few seconds, I should have the same prompt generating an image where now we apply a specific style. So let me go over to the instance here and type Docker logs, and it should show me, okay, yeah, prompt. In the logs of that container, it says retro arcade style, a photo of an octopus playing chess, 8-bit pixelated, etc. And so it will generate now an arcade style of an octopus playing chess. And it certainly reminds me of some of those video games some of you might have played growing up with old school graphics. And so you can play with the prompts or with the style here. Does anyone want to suggest a different animal than octopus? Any suggestion from the audience? I'll take a... Okay, flamingo. I heard flamingo. All right, so photo of a flamingo. And let's see what happens. So preparing for the next request, what game should we substitute chess with? Go? Okay. Playing Go. I like that. So let's see. If I type in Docker logs, we'll see, all right, retro arcade style photo of a flamingo playing chess. Okay. Flamingo. And as you'd expect, it would play chess with its feet, not with its wings. So pretty good. Let's go and change it to Go. But actually, let's play around and pick a different style. So on this web page, is there a style that tickles your fancy here? Someone can call out a style as they see one that they like, and we're going to use that. Assuming it's large enough. Anyone want to interject? Okay, I'm going to pick one for y'all. So let's pick graffiti style. All right, so I'm going to go to this file, look for graffiti, and I'm going to copy the style definition into this cell. All right, so we're going to hit play here, and we're going to generate a brand new image of a flamingo playing Go in a graffiti art style. All right, so let's see what happens here. So you can play around with style, prompt engineering, all of this, while your OctoAI endpoint is launching. So I'm going to go ahead and click again on View Event History. Sometimes you might get an error here as you navigate the OctoAI website UI, and the solution here is just to hit refresh. And if hitting refresh doesn't cut it, you might have to perhaps click on the endpoints icon again. I suspect there's a lot of people right now interacting with the service, so we'll see what happens if I can successfully. Okay, so there seems to be an error. I'm going to go back to this link. But yeah, go ahead and play with this, and look, we have a flamingo that looks like, you know, graffiti style. Unfortunately, the actual playing Go piece has been kind of cropped out for some reason. So sometimes it doesn't always produce the best results, but hey, there's a seed parameter here, and we can change the seed. So I can set seed to 10, for instance. I'm going to use a different seed, and maybe I'll get a bit more lucky. So there you have it. This is the Play with SDXL Styles session. And then once we have your OctoAI endpoint up and running, for some reason I'm having issues right now with the website, so bear with me. But I can also provide you with a link to an endpoint I started ahead of this lab in case you don't want to wait and you just want to get started. I can give you an endpoint link. I'm going to put it on Discord. And so you can start the other sections of this lab here where we can test the SDXL container served on an OctoAI endpoint. Okay, so something is up. 1 second. Luis, can you check if we can access OctoAI right now? It seems like it's unresponsive. Okay. All right. Looks like we're having a little issue. A good thing we have redundancy set up here. The trick to continue this lab is that you can rely on your locally running container for the next session of this notebook. So usually what would happen in this other section E, I realize I have 2 section E's. In the second section E, you're supposed to overwrite the SDXL endpoint URL with the one that you get from the OctoAI website. So let me access my endpoints here, the SDXL one I launched. It seems like our website is having some technical issues, so. Well, that is getting sorted out. One thing I can do is just remove this assert. If I remove this assert, I'm just continuing to use the container that's running locally on my AWS endpoint. In this section, we should be switching over to the OctoAI endpoint. But because I'm having some issues with the OctoAI website, we can go ahead and proceed to using just the locally running container. All right, so I'm going to run this cell here again, and that should give us the exact same image. Because what would have happened here is that I'm switching from localhost to this SDXL endpoint. But unfortunately, it seems like the website's having some issues. Those are the joys of live sessions, so bear with us while we get this resolved. But yes, feel free to remove this assert and just continue along here. We're going to start to actually test the clip interrogator model on the Mobi logo. So we've already brought up a clip interrogator endpoint for all of you to use. If you're trying this tutorial after today, we have some instructions on how you could do this on your own on OctoAI. So I'm going to go ahead and run this cell here. All it's going to do is grab an image of Mobi and display it. And we're also setting the clip endpoint URL to point to the one that I prepared for you all for this lab. Next, we're going to go ahead and send a request to that clip interrogator model. All we're sending basically is the image in a base64 encoded string. And we set the mode to fast. This is going to ensure that we get the fastest responses from that model endpoint. I'm going to go ahead and send that payload over to the clip endpoint URL. And you'll see that right away it actually gives us a fairly fast response. It will say that it sees a whale with a container on its back. And it contains a lot of other descriptors and qualifiers. But if we just keep the first entry in this comma-separated list, we get a fairly accurate description, a textual description of what it sees in this logo. So this AI has recognized fairly accurately what it sees in this picture. I'm just going to trim that response a little bit to shorten it and just keep the first entry in this comma-separated list. And now we're going to send it back to the SDXL endpoint. Now, usually at this point in the lab, we'd be using the OctoAI endpoint, but I'm just using the locally running container on my AWS instance. And at this point, what I should see is that whale with a container on its back, where I've applied a cinematic style being rendered by SDXL. Okay, so we get an interesting image here. It's gotten the whale right. It actually looks like a killer whale. But the container, instead of a shipping container, what it understood it to be was maybe a food container or something. And for some reason, it hasn't placed it on the back. So interesting, interesting rendition by Stable Diffusion. One thing I can do is set the SDXL payload back to, so the, let's see, the seed. If I set it back to 1, I think it should give us a better image. As you can see, as you change the seed, you're going to get a different image every single time. So you could do this 1,000 times and you're going to get 1,000 different images, which is where the sort of addictive component of playing with Stable Diffusion comes in, because you're always waiting to see what kind of great image you could generate. So this one is much better. I just changed the seed, and sure enough, we have a whale and a container on the back of the whale. All right. So let's take a look at OctoAI. All right, we're having some slight technical issues. So what I'm going to do here for the folks who want to continue with the lab, I'm going to give them an inference endpoint URL in the Discord. So please go ahead and use this URL for the SDXL endpoint that I've provisioned for you. Yeah? Can you do a health check? Or, yeah. And I see some folks are able to keep up because they've generated some beautiful images of the whale. Yeah. All right, 1 second. Let's see. So let's see, how can I do a DM? You know what, I'm just gonna drop it in here and test it out. Yeah. Okay, doesn't exist yet. It's launching. Docker. Oh, SDXL. That's why. Yes. Okay. So let me do this. So yeah, I'm going to share with you all a URL in case you're having some trouble proceeding with the lab. This is something that you can use starting in section E. So I'm going to do that with you again. So in E, I'm going to uncomment that assert, and I'm going to paste this here and take a screenshot so people understand where this fits. But I'm hoping everyone's having some fun with generating interesting prompts. I can see that people are definitely creating some original images here, so that is great. All right. Okay, so if you're having trouble with OctoAI, just go ahead and use the link that I've prepared for you and paste it in the cell. Penguin building an atomic bomb. Could you add it there, please? Yeah, thank you. Okay, so if I run it again, what this should give me is, oh, of course I shouldn't have just plain text in my cell, but I'm going to run this SDXL inference against the OctoAI endpoint address that I shared with you all. But if some of you are more successful than me in launching your OctoAI endpoint, please do use your own URL. But this is a backup in case you're running into issues, so you aren't left behind as you try to complete this lab 1. All right, so I'm going to hit this endpoint here with an SDXL request. So we've already gone through clip, and I've shown you that we can actually take an image and produce text out of it using the clip interrogator. Let's see what happens when we feed that. There we go. Okay, so this endpoint is working great. Seamless transition from the locally running container to that cloud-based OctoAI endpoint. We're getting the exact same image, which is what I love to see. So we've already gone through clip interrogator. What we need to go through next is Llama, which is our LLM, our large language model. Think of it as ChatGPT, but an open source version of it, which is still just as powerful. So I've given to you, all lab attendee members, a Llama 2 OctoAI endpoint, so you don't have to launch your own. If you do this lab after today, there's some instructions on how to do it yourself. But I've already prepared this for you. Now, what we're going to do here is that we're going to take the output of the clip interrogator model, which identified the input photo here of Moby, to be a whale with a container on its back. And I'm going to do a little bit of prompt engineering to set that scene into outer space. So the Llama prompt here is going to be in a single sentence, because I like this to be concise. We're going to insert the user prompt. So set in outer space, colon, the clip labels, which is a whale with a container on its back. So if I run the cell, sure enough, and we print the Llama prompt, it's going to be in a single sentence, set in outer space, a whale with containers on its back, and then the response is left blank. And so the Llama 2 model is essentially going to try to autocomplete what fits inside of that response. I'm going to prepare the Llama 2 inputs. You don't really have to change this here. There's not something that you have to edit, but essentially there's a system message that tells the bot how to behave. You know, for instance, you're a helpful bot. Please appropriately respond to this request. And then the user message, which contains our Llama prompt. I'm going to go ahead and send this over to my Llama endpoint, and let's see what kind of story it cooks up. So within a second or less, it gives us a nice story. As the spaceship soared through the cosmos, a majestic blue whale gracefully glided through the void, carrying a shimmering silver container adorned with a glowing symbol on its back. All right, so he gave us a pretty detailed sentence describing Moby in space. And now what we're going to do is we're going to take that story and feed into SDXL and see what happens. Let's see how SDXL handles that request. So at this point, we should have an updated picture that sends Moby into space. And again, this will take a few seconds to produce an image. Let's see what we get. Can I get a sense of who's roughly at the point I'm at in the notebook? Raise a hand if you've already gone through the Llama 2 section. Okay, so I think everyone's going at their own pace here. About 10 to 20% of the room is at this stage. And so let's take a look at the picture. So we have a really interesting space whale here. It's somewhere between ocean and space. So it's interesting that based on the whale prompt, it's determined that it should be still grounded in some ocean, photo of the ocean and the sunset. But if we look at the sky, sure enough, it is covered with stars and galaxies. And what's interesting too is that it looks like the whale is kind of turned into a spaceship. Maybe it's fused with the container. You can play with different seeds. You can adjust the prompt a little bit. See how this affects the picture that you produce. But we've lost the container side of the picture. So in Lab 2, you're going to learn how to get better consistency here if you get to this Lab 2 stage. So that completes the very baseline OctoShop flow, which takes a clip interrogator model in order to produce text based on an input image. Then you feed that text into a Llama 2 model that will produce a story to feed into the stable Diffusion XL that all of you, hopefully by the end of the lab, will be hosting on your own OctoAI endpoint. And so to recap, I've provided the entire OctoShop workflow into this helper function. All you'll need to do here is replace this line, and paste in your own OctoAI SDXL endpoint URL. Otherwise, you're going to run into this assertion error. So I'm going to run this cell. This is just the helper function. But now we're going to call it in this cell based on an image URL, a user prompt of setting an outer space, and a style of SDXL, which you can adjust. We're going to send all of this, and we're going to see what we get back. And that should be, hopefully, the same image that we produced in the last stage. But now we have essentially the entire pipeline run into a single self-contained function. And sure enough, what we should see is the clip interrogator output, which is a whale with a container on its back. The Llama 2 output, which is a story that it concocted based on that user prompt of setting Moby into outer space. And at this stage, feel free to change the image URL. Feel free to change the user prompt as well as the style to customize your OctoShop pipeline. So this is really where you can have fun and customize all of this to be something truly unique. So for instance, I want to create a bot that sets pictures in ancient Egypt, for instance. So I'm going to say set in ancient Egypt. I'm going to customize the style, so user style. I'm going to go back to my Moby doc. the MobiDoc page to get some inspiration. So maybe I want it to be more digital art style, so I'm going to go ahead and look for digital style, which is, I think, contained in the stxl styles underscore sai.json, digital art. I'm going to copy and paste this into my lab cell. That's going to give me this digital style applied to this prompt set in ancient Egypt. So let me rerun the OctoShop workflow now. And I basically created my own unique workflow that sets pictures in ancient Egypt. So I expect you all to customize your own workflow by changing the user prompt and the style to get something fairly unique looking or fairly original. So it could be your favorite movie, your favorite country, your time and place, maybe something a bit more sci-fi, maybe your favorite video game universe or fantasy universe. And within a few seconds, just because we're invoking each model back to back, it should give us an interesting image. And at this point, we've completed this Jupyter notebook, and we're ready to start building our Discord bot. And this is what I'm going to walk you through next, once I'm able to get this image back. It's possible we have a lot of people hitting the endpoint at the same time that I've provisioned, so it's quite possible that this is taking a bit longer than usual because many of you may be using the same endpoint that I provisioned for all of us to share. I did set the number of replicas to be 20, so I've scaled it up, but it's possible we just have more than 20 attendees and we're generating a lot of images, so just bear with me while this is generating. All right, so I'm going to go ahead while this is running, and we're going to go back to the instructions. If you click at the bottom of this link, and we're going to set up a Discord bot account. So this is something where we've provided very detailed instructions, and so hopefully it should be fairly on Rails. What I'm going to do is I'm going to click on this link, copy the link, and paste it in my browser. I'm on my laptop here. I'm going to create a new application. I'm going to call it, keep in mind that we have to follow this convention, so DockerCon 23 Moreau Thierry. And I invite you all to create your own application based on this naming convention, last name, first name. Then you hit create. At this point, you're going to need to reset the token. So we're going to go to bot. We're going to hit reset token. Yes, do it. And we're going to copy the token here and save it somewhere. So I'm going to save it in my VS Code. So please store this somewhere where you can access it later. Once you've saved your token, you're going to scroll down, and there's a toggle on message content intent that you're going to turn on. You're going to save the changes. This, again, is all described in the instructions. I'm just running it live, but you can just follow along from the instructions. Under the side menu, if you go to OAuth2, URL generator, you are going to have to check the bot box. And you're going to scroll down and enable some bot permission. You're going to enable send messages from the bot, attach files, and use slash commands. All right, so these are the 3 things that you're going to need to enable. Again, we've provided some screenshots for easy guidance. And then you're going to take this generated URL, and we are going to copy it in this spreadsheet that I've linked here in the instructions. This spreadsheet where you've already entered your name, you're going to scroll to the column on the right and provide the link here. We have Tim, our IT support person, who's been a real hero to help prepare this lab, who will set up the Discord bots. So Luis, I think it's a good time to let him know that we should enable the workshop participants
to post their bots onto our DockerCon bot channel. Luis? Yeah, okay, perfect. And so hold on to this link for now. Once you see that next to your link, the status is accepted, you can proceed to pasting that link into a browser. So it might take a few minutes until this bot status is accepted here. You're going to enter that link into a browser once you see the status to be accepted. You're going to select the server here, which is going to be OctoAI, continue, leave all the boxes checked, authorize, and that should allow us to then deploy your very own bot onto our Discord channel. But we're not quite done here because we still have to build the Discord bot container locally that contains all the code to run the bot. So going back onto my terminal, you have to make sure you SSH into your EC2 instance at this stage. I'm going to go into the Discord bot. And at this point, you can actually personalize your bot under the workflow file. So what I'm going to do here is I'm going to personalize my bot under the workflow file. And at this stage, I'd like to actually change the prompt to set in ancient Egypt, as I did in my notebook. Seems like there's an issue here. Set in ancient Egypt, and then I'm going to copy the style here to be digital art. So I've customized my OctoShop workflow. And then going back into my instructions, I'm going to build the bot container image. This should be a lot faster because we're not relying on any deep learning libraries. All the deep learning complexity and deep learning libraries are behind that endpoint that you all deployed. And what I'm going to do next is run this command. Now I need to paste that into a text editor because you need to customize it with your Discord token, your unique command name, and your SDXL OctoAI endpoint URL, which by now should have been launched and up and ready. But if that's not the case, you can always use the URL that I've provided you with. So I'm just going to go and open a new text file. I'm going to paste my Discord token that I set aside. My command name, I decided to name it Mummify in reference to ancient Egypt. And just go into Discord. I will go ahead and grab the URL that I shared. I can see there's a lot of really great submissions so far. So I'm going to go ahead and grab this URL here and paste it here. And then I'm going to copy this command and enter it in my SSH terminal to launch my bot. So that should launch the bot locally on the EC2 instance, but that's enough for us to power the bot for the duration of this workshop session. So by now it should be up and ready. And at this stage, if I go to if I go to DockerCon 23 bots, and I do //mummify, sure enough, there's my command here that I just created. And let's see. I'm going to go with a picture of a cat. And let's see if I can set that cat in ancient Egypt. So it says it is thinking because it has to send it through the different models. So we just have to wait a little while. But sure enough, we have a cute looking cat, as you can see. So we've got the image back. And sure enough, we have the Great Pyramids in the background. It came up with an interesting story, which is, let's see. So the clip interrogator identifies this photo to be a kitten sitting on the floor or the ground looking at the camera, which is accurate. And then Llama 2, based on the prompt that I hard-coded, came up with a story. So a fluffy kitten with bright green eyes sat regularly on the desert sand, gazing up at the camera with a curious expression. Okay, so it kind of hallucinated here a little bit. It lost a bit of the ancient Egypt theme. But interestingly, it still managed to get ancient Egypt. So anyways, experiment with your bot. Hopefully you're able to launch it. Our colleague Tim is going to make sure that every one of you is able to have their Discord bot accepted. So once you see accepted, you can go ahead and build the bot and deploy it. And that should allow you to, deploy your Discord bot in this DockerCon 23 bots channel. And you can see some of the things that we've built in the past. So Luis with the Mona Lisa, sending the Mona Lisa to space. That was my ancient Egypt one, which creates a very interesting old boat that has two tails. But if you look at the surroundings, it does look like the Nile. And it looks like one of those traditional wooden boats from ancient Egypt that they used to carry heavy rocks and granite across the Nile to construction sites. So there's some accuracy. You'll notice that there isn't very strong consistency between the input and the output photo, and that's because we're not using control nets yet. And we're going to learn how to do this in Lab 2. So this is where my walkthrough section ends. And I'm just going to flash the schedule here while you all go at your own pace through Lab 1. And I guess I've used up all my time. But we have a break coming up, and we can adjust the schedule accordingly to make sure everyone has had the time to go through Lab 1. The way you can think of Lab 2 is essentially a component for those who didn't feel challenged enough in this Lab 1 and would like to go further or get their hands even more dirty to do some customization. There's more of an open-ended coding component to Lab 2, whereas Lab 1 was very much on Rails. Lab 2 should have some, gaps for you to fill in the source code of that model container so you can add your own control net in the mix. So we're probably going to start a break in 3 minutes for you all. But what I'm thinking is that we can use parts of Lab 2 for those of you who haven't finished Lab 1 to just complete Lab 1. And you can always keep Lab 2 in the back of your pocket if you'd like to try that on your own later on. But I think the most important thing for everyone here who is trying to participate and keep up with the labs is just to finish Lab 1. So you've completed the entire flow. You have your unique Discord bot that you can show and share to others. And then for the overachievers in the room, you can follow along with Luis Vega in about 15 minutes how to go through Lab 2. It's going to be a lot less hands-on than what I did, where he's just going to give everyone an overview and then let people go through Lab 2 at their own pace. All right, so if you have any questions, ask them on Discord so we can encourage virtual participants to also be included. But we're going to have a Q&A at the end of the morning session. So thanks, everyone. Hope it went relatively smoothly. And we'll resume in about 15 minutes or 17 minutes. Thank you.
Okay, so I hope you guys enjoy your break. So now I'm going to be basically talking about Lab 2. And for Lab 2, we want you to know that this is basically, I want to show you guys how this whole workflow works for control nets. But we really want to have you guys finish Lab 1 because we believe that's very important. So today I'm going to do Lab 2 very quickly to some degree. And I'm going to explain and go through the steps. But I don't, if you guys haven't finished Lab 1, I encourage you to actually finish it first before going to Lab 2. Because Lab 2 is going to get a little bit confusing if you don't do that. So let's leave Lab 2 if you don't get to finish Lab 1 as a homework or something that you can do later today or tomorrow, right? In case you want to check how to do this thing, all right? In case you haven't finished Lab 1. Okay, so So as Thierry pointed out early on, for Lab 2, basically what we want to show you guys is the power of ControlNet, right? So far, we have been able to generate images with stable diffusion, and we have been able to generate really cool prompts using Llama 2. But these images are really not following the composition or the contours of the input image, right? And one of the things that we would do to do that is ControlNet. So here in the documentation, we have a little bit of background on ControlNets that I invite you all to go and read if you are interested on this. It's pretty cool. It covers what are these kind of networks, and that together with what Samir covered early on. But let's head down to the thing, right? So the first thing that we are gonna ask you to do, or is piece of this workshop for ControlNets, is basically on section 1, we will extend now the model container, right? The model container that we built, that we have in Lab 1. In Lab 2, we basically have another folder with model.py. And this model.py file contains a bunch of to-do comments. So if you head down to Lab 2 folder, XEXL Canny, you can see that the model.py file contains a bunch of to-do here, right? And these to-dos are the things that we want you to start experimenting with, just to get familiarized on how to build these pipelines, basically. So in these to-dos, for example, you'll be using the ControlNet class, you will use the VAE class, and then you would declare like a ControlNet pipeline in the piece of the constructor of the model class. And then the other thing that is going to be required is basically inside the predict, you guys will basically invoke that pipeline that you just built in the constructor, right? So in order to do that and guide you on how to do this, basically here there is a use the following link bullet point where you can click on the link. And this takes you to a place where it talks about how to use SDXL ControlNet Canny within the diffusers library. And in here, right at the bottom, you will see that there is some code snippet, right? And in this code snippet, there is a way of how to use the VAE, for example, how to declare it, how to declare a ControlNet XL pipeline, and how to declare the ControlNet itself. Remember that there are different kinds of ControlNets. There are ControlNets that are based on posts. There are ControlNets based on depth map, and there are ControlNets based on Canny. But the one that we'll be talking today is based on Canny. This is the simplest of the ControlNets, if you will, and it's the one that we're going to be using today. All right. So basically for this, piece of the section, all you have to do is basically fill those to-dos in that file. And I already did that. So I have here VS Code open. And in here I have that model py with those things filled out, the VAE, the pipeline, and also the ControlNet. And also the pipeline with all the arguments on it. What we're going to ask you to do in section 2 is basically to build again that container, right? So I'm going to do it. I already cached this, but I'm just going to show you how it will look like very quickly. So I'll go just head down to Lab 2, SDXL Canny, and then you do docker build -d SDXL Canny dot. And in this case, I finished very quickly because I already pre-built it. And you can verify that your image is there by doing this command. And you see that, this is the image that we have there, and we just built. OK, so once we build that image, we're just going to run that Docker container. So we're just going to do this. And now if we do Docker PS, we see that this container was just created like 2 seconds ago. So now we can basically get the logs and see if the pipeline and the thing has been initialized correctly. Let's see, it's initializing. So now we get this message here saying that SDXL canny pipeline has been initialized correctly, which means that our container is ready to roll. One quick way of knowing if things are up and running is like we have an endpoint called health check that we can just curl if we want to. So we can just do like curl localhost 8080/health check. And it says like healthy yes. So if we get that, it means that the container is ready to go, right? So once we have that container built, we go to section 3. And in section 3, what we're going to do now is basically launch our notebook for Jupyter Lab. And it's going to do that under the Lab 2 folder. So one level up, we go and run that container, that notebook. And right now, my computer doesn't have pull forwarding because I haven't set it up, but I can do it here quickly for you guys. So, so let's do that. Localhost, I think it's 8080. Localhost 8080. And we do DockerCon 23. So with this command, basically what I'm doing is like creating a tunnel between my computer and AWS instance so I can see that Jupyter notebook inside my computer, right? This is the same thing that you guys did for Lab 1. So now I'm going to be able to click this, and Jupyter Lab should be opening, right? So if I head down to Lab 2 in here, then we'll see the Lab 2, right? The whole thing about the control net. So the first thing that we're going to do on this lab is basically, load a bunch of boilerplate libraries and functions that we're going to use. If you see this token warning, don't worry, because all the endpoints that we're using today are all public. So this is just a warning saying that you need a token in case you're talking to private endpoints. But today, for today, all the endpoints are public. Okay, so the first thing that we're going to do is that we're going to load the Mobi image. So the image that we show the gallery for, right? And this is the image that we're going to use as an input, and the one that you guys use in Lab 1. And here, I want you to see that, for the XDXL payload, we now have a bunch of new parameters, right? So we have this thing called control net conditional scale, as I'm highlighting here. And right now, that is set to 0. And when you set that thing to 0, what you're telling the pipeline is that ignore the control net. Basically, the control net is not going to have effect. So when you set it to 0, you're doing basically most of the things that you did in Lab 1. And we have a bunch of, we have 2 more parameters. One is a start and one is end. Often, you start the control net process always at 0, but you can play with when it ends. So 0.5 means that you just run it for 50% of the time. So let's run this and see what we get out of it. And as you can see here in the URL, we are testing this container locally in AWS before actually doing anything else or deploying it. So let's wait and see if it when it finishes. Let's see. Let me check very quickly here to see the logs and see what's going on. Logs, SXL canny. Yes, so we see in the logs that something was just generated. So if I go back to the, let's see, why it's not displaying? Should be there. Oh, there you go. Oh, oops, okay. Okay. Let's see. Yeah, let me rerun that thing again. Just wait a second. Let's see if that thing is being run. It is. I don't know why. Yeah, it should be running. It is running. Just finish. Okay, so now we get the image, right? This image, as I said, has we set the parameter, the control net condition and scale to 0. So that means that we're not really applying the control net, right? So in the following cell, what we're going to do is basically set that parameter to 1.25, right? So we're basically going to the whole stream of using applying that control net all the way up, right? And to see now what happened. And when we do this for this kind of pipelines, what we're going to see is actually a picture that will be very kind of close to the input one. Maybe some colors will change, but like there's nothing really creative or interesting about it, right? You see this? It's basically almost there's like the diffusion process is not really doing much. So what I'm trying to tell with all this is that basically the number that you want to have for the conditioning scale have to be something in between, right? Not all the way up to 1.25 or 0, which you're not using control net at all, but actually something in between. So one number that a lot of people in the community use is 0.5, 0.6. It depends on like how much in your workflow you want the input image to basically condition the output that you create, right? So right now I'm running it with 0.5, and with this payload, and you see that you get the whale in a photographic scene, and you see that the containers, there's some of those containers up there that follow the same contours as the input well, right? So this looks pretty similar to the actual icon, and not to this one, right, where control net is not being applied. Okay. So now we have learned like how to test this control net pipeline, also like how to set these parameters, and now the next step is basically to upload that into Docker Hub. So as I said, I wanted to make this quick and easy. We also, I think as Thierry did for lab 1, we have a pre-built Docker container here that you can use in case you don't want to build your own later on. So I have already build and push an image in Docker Hub. So if you see, I think somewhere here. Yeah, here. So I have SCXL Canny repository here. It's public as well. People are open to use it. And I have here a tag with 0.10, basically, of that being pushed. Also, I have already an endpoint, with that container being deployed into our platform, and I set a min replicas and max replicas to 1, and that container is ready to rock and roll, right? It's running here, getting solid blue, and so these steps are already done. So after those things are completed, what we want you guys to do is basically copy this URL and head down to this cell where we're going to test now that container, no longer running locally, but actually in our cloud. So we're going to change this SDXL URL, endpoint URL with your own one. And if you don't do that, there's an assertion here that's going to be triggered, basically erroring now and say, hey, your thing must be different than just localhost, right? So we're running it right now. And we should be basically expecting to have a similar result to what we had here up, because we are basically sending the same payload with the conditioning scale set to 0.5. We are not changing anything. The only thing that we are changing in is basically where it's running. So right now, this is actually running on OctoAI. It's no longer running on AWS. So you see that I was able to get a beautiful picture of the well that I just made with that prompt, right? Okay, so now in the following cell, all we do is pre-package all of this workflow, basically as a single function that you can invoke, just not to use for wells, but to use with anything else. So, so in this OctoShop function contains all the steps in the pipeline. And what we're going to do now is basically run that work. Oh, yeah. So, yeah, in this function, You also have to change the SDXL endpoint. So it's no longer localhost because now we're running it in our cloud. So you have to set it with your custom OctoAI URL. And once you do that, now you can actually run the OctoShop. In this case, we are changing the style to be, I think, a cinematic is what we're doing there. These styles are the same that we, that we took from that list that Thierry was showing early on. And we should see an image anytime soon. There you go. Beautiful, right? So this not only looks closer to the icon that we saw early on, but actually has some creative, taste on it, and like different colors and different styles. And this looks very beautiful. Looks like very close to what we were trying to accomplish. But the thing doesn't stop with just Moby or Docker. We can also use the same technique on humans, right? Not only in animals. So as we said earlier, we're gonna run the same thing, but actually with the Mona Lisa. So in here, we are getting a picture of the Mona Lisa as an input instead of the Docker Moby icon, and we're going to use that to basically run the control net and do the same, do the same pipeline, the OctoShop pipeline, right? So what we should expect out of this is another image with a person with a similar pose as the Mona Lisa is in this photograph. But as we know, you see this person that is just show up here with this particular, I think, let's see, the prompt. We're using the same prompt of cinematic prompt. Yeah, we're using the same prompt as the one that we use for the Docker icon. And you see here, we're doing this in outer space. And you see that the contour and the shape of this person is very similar to the Mona Lisa, actually. But the face is still not the Mona Lisa, right? Because all we are telling Stable Diffusion is like, hey, fill all this, basically the blanks, right? But like the face is not gonna be the same, right? So one of the things that we are telling you how to do is basically use a technique called face swap to now add the face of the Mona Lisa and basically put it into that picture. So you basically can, imagine people in different settings, right? So we did that here in a single function right at the end. So we define a face swap function that we're going to do the swapping. And this function takes as an input the source image, which means that the image that contains the face that you want to swap, and then the target image or destination image, which is where you want to put that face. So as an input, we will put the Mona Lisa, and as an output, basically, is going to be the one that we generate in SDXL. And so if we run this, you will see that we will create the same person that we did above here. But then we are also going to paste, if you will, the face of the Mona Lisa on that person. So as you can see here, this is the outcome, right? Beautiful. It looks very real, although even though you're in outer space. But this looks closer to our actual input, right? And this is the kind of magical things that we want you guys to learn with these workflows, because we know that in order to build really great things, it's not just about just using a Stable Diffusion XL as it is, as it comes, right? It's really about the creative ways that you can use a Stable Diffusion and the kind of workflows that you guys can create and customize. And this is what we are OctoAI are very excited about allowing you to do, basically, to basically build this complex pipeline so you can actually create great value for folks out there. All right, so this is basically it for the Jupyter Lab. So what's going to happen next, and this is the section 3, right, is that, yeah, you can go ahead and stop the container and do the stuff. But we also, besides just doing and showing you lab 2, we also prepare for you a Discord bot code. So if you see in lab 2 folder, there is another folder called Discord bot. And in this folder, we have the bot code, and we have the workflow, which is this workflow, the Octoshop that I was just showing you. And in this workflow file, it contains all the invocation to make that whole thing, like get the person as an input, create an image similarly and similar, and then like swap in the face, right? So in order to do that, really is similar to how we did in Lab 1. So all we have to do is go to Lab 2, then head to Discord bot. And what we're going to do is, I think I have that bot here, but let's see if we build it again. So I do, you build the bot code is another container. And then all you have to do is, let's see. As we have in the documentation, in order to run the bot, this is how you build the bot, right? In order to run the bot, you have to have all these environment variables, basically. The first environment variable is the token, the Discord token, right? That you get when you create a new applications, as Thierry showed. The command is like the command you want to use. And the SDXL endpoint is the one that you just built and you're going to build later on. So I think I have a version of that somewhere here. Let's see. What? Yeah, I think I have run this in the past. Maybe I need to do this as well. Yeah, you also need to have the OctoML token. I think there's a missing piece there. Well, I think, yeah, in this case it doesn't matter because this is open, but I'm just going to paste it just in case. Cool. So let me show you how it works. Bear with me. Probably about, yeah, it's better. The container is bot. That's my Discord token. And then all I have to replace is my SDXL endpoint. In this case, the one that I created, it was in OctoML. It's this one right here. So I just paste that. And all I'm going to do now, and the Discord command I'm using is just canny. So all I'm going to do is run that. And one way of knowing that our bot is actually running is that we will get that little log here, text saying it was sent, and then it's like one command, right? And if you're interested in how that gets printed, then you go to Discord bot and then bot. And you see that right here in the onReady function, we basically, that's the thing that is get executed once the bot is launching. So that's how we print in that, that thing, right? And it's just counting the number of commands that you have registered. So now this is running, right? So it means that actually if I go to our Discord in DockerCon bots, it seems that there is some people already posting stuff, which makes me pretty happy. I consider this success. So I go and type my command, which should be displaying anytime soon. And then I'll take an image as an input. I have the Mona Lisa here, just for the sake of replicating what we just did in the Jupyter lab. I'm going to be running that. My bot is creatively named Foobar. So if you guys see that, that was the one that we used in today's session. So right now it's saying thinking. These are, by the way, all these status messages are all messages provided by the discord.py library, which is what we are using to interact with Discord API. This is just a Python package provided by Discord for folks to basically create their own bots and deploy to the Discord platform. OK, so it seems that we got the Mona Lisa. This is the stuff that we just built. We got the Mona Lisa as an input, and we get the as an output. And we can also see here, as Thierry was showing up, what was the output of a clip interrogator, and also the Llama 2 enhanced prompt that we are using to create this beautiful and astonishing image as an output. So this is it, I believe. Let me check in the documentation just in case. But yeah, this is pretty much, we'll cover what we wanted to cover for Lab 2. Basically, for you being able to deploy this workflow in OctoAI and also use it in a Discord bot and just test it in our own channel. So after this, all we ask you is to pause your OctoAI SXL endpoint, and that's pretty much it. Thank you. Any questions?
Test. Okay, great. Well, let's thank my colleague Luis here for the overview of Lab 2. So we covered a lot of information. I'd like to reiterate something I said on Discord and said earlier that this Lab 2 here is, again, a stretch goal for the attendees. Try to complete your Lab 1. I'm seeing a lot of Discord bots already on Discord, so I'm just gonna leave, is it okay if I leave this window here?
Yeah.
Showing some of the activity here from folks who attended this workshop and managed to get their baseline OctoShop Discord bots up and running, and we can see a lot of really cool and interesting effects. And certainly the one that Luis just showed is using ControlNet and FaceSwap for consistency. So there's a lot more consistency between input and output images. But for all of you who are still completing Lab 1 here, you're still going to have some really amazing generative AI bots, and we're seeing a lot of really creative ideas being showcased in the DockerCon 23 bots channel. So keep working on your Lab 1. We are about half an hour away from the end of today's workshop, but I wanted to address some questions that were asked on Discord. So how long will those endpoints that I put up for you to run through the Python notebook and build your bot? These endpoints will be available till the end of the day, around 9 p.m. Pacific. And we might decommission the AWS EC2 instances sooner than that, because we just get billed for all those instances as long as they're running. We're going to have to decommission them. But it turns out that for the IPython notebook and for the Discord bot, these are something that you can, these are pieces that you actually can run from your laptop as long as you're not building a container and testing the container on your laptops. So if you'd like, you can continue to experiment as long as the OctoAI endpoints are up and running with building your own bot. And we'll provide you with links to endpoints that you can just use here so that you don't have to be billed on OctoAI. You already have some free credits, so you should be able to comfortably go through this lab yourself. But of course, we encourage you to try and use OctoAI to build some really cool and exciting generative AI web applications or bots, etc. And with that, I think we can probably disband for about 15 minutes. Some of you can finish your Lab 1 bots, try to customize your bot further to get some interesting effects or interesting transformations. And I think we're going to reserve the last 15 minutes for some closing thoughts. And of course, a live Q&A session. Maybe we can pull 1 or 2 questions from Discord. Do you want to bring up the post-class survey? Yeah, okay. So my colleague here, Samir, will also ask you all to send and submit the post-class survey. We'll appreciate a lot of your feedback. This survey is really important for us to improve this workshop. Keep in mind, actually, that this is the first time we've organized this specific workshop. So we've learned a lot from today. Your feedback will be very important for us to improve that experience. I'm glad at least many of you have managed to build and complete your bots, but there were some hiccups along the way. And so we'd love to learn about some of the maybe frustrating aspects of the lab, some of the more pleasing or exciting or educational aspects of the lab that you can share with us. So Samir, please go ahead and share your survey with the rest of the group.
Sweet. So this should only take 30 seconds to do. It's completely anonymous, so we really would appreciate any feedback you have. And obviously, we're going to use this to just improve the class for future deliveries. So since we have about 30 minutes, I'm going to give you guys just a minute or two to try to get this done, whether you're in person or online. And then I thought we could actually just jump into a Q&A discussion for maybe the last 15, 20 minutes, and then just kind of end a little bit early if you need to, as opposed to taking a break and coming back. All right, so I will give you guys a minute or two to kind of get this done, and then we will go into a kind of a live Q&A and discussion. All right, guys, let's get started with the Q&A. So you already know, you know me, you know Thierry, you know Luis. All of us work at OctoML. We have another person here who's Ajeet, who is a Docker captain. So he is the deep Docker guru. I'll have him introduce himself really quickly so you know his background as well.
Yeah, hi everyone, this is Ajeet here. I'm based out of India. So I have been part of the Docker community since last 7 to 8 years. And it has been great compiling this whole workshop. But if there is any Docker specific queries, just let me know if I could answer.
All right, cool. I am also going to open up Discord in the background here so I can kind of be watching for questions that might come in through there. So also just like recap, we saw in the pre-class survey that like half of you guys are developers. You guys like are pretty good with like comfortable programming generally, relatively new to these specific ML models. I think that like one good thing about generative AI is you actually don't need to learn a ton about the deep architecture of these models, and you can finally actually be working at a way higher level where all you really need to know are like what are those like 10 or 20 parameters, like prompt or like a guidance scale and things like that, and essentially just you can start using it for inference. I think where things get a lot harder are as if you start doing things like updating weights in a model or like fine-tuning it or doing stuff like that. You also saw today that doing ensembles of like a workflow of models is like relatively easy to pass things forward. So, all right, who is brave enough to shoot the first question? Go ahead. The question is about data drift. So every time you, yep. Every time you run the model, you want to check for the drift detection on the data. Which data do you mean? Like the pre-training data or like the inference data every time you're calling the model? Actually, that might be great. Yes. Cool. Thank you.
Yeah. Okay. Okay, thank you. First, thank you so much for the presentation. I really enjoyed. My question is related to the data drift, consent drift, explainable AI problems. When we deploy our model, we want to know what is happening with the data, with the input data, with the prediction, and even we can or we want to generate some explainable AI algorithms. I would like to know if possible to add this drift detection into your platform in the model that we deploy using OctoML.
Yeah, so that's a really interesting question, which hints towards kind of a more data-centric service that we can offer alongside our compute service, right? Because I think what's really interesting about real-world AI or ML deployments is to kind of monitor the usage over time, the data that's going in and out, and especially how the users of the clients of your model are responding to the data. Like, is this a good output? Is this a bad output? For instance, we've seen image generation. Could some of these images be flagged because the content is inappropriate, right? And monitoring sort of the behavior of the model over a long period of time, I think it would be very valuable to actually be able to offer that as a service on top. And so that's certainly something that could be offered in the longer run, because what you can do with that data is now fine-tune the model to correct the behavior. And we see this, for instance, for anyone who's used ChatGPT. Every time you get an answer, you can do a thumbs up or thumbs down. There's all the history saved. So I think it's a really interesting idea. Today, OctoAI is mostly compute-centric, but we're starting to add features that are a bit more data-centric, like the ability to store different model assets, et cetera, which we call asset lake. And down the road, also being able to monitor data. So definitely a really interesting idea. I mean, we should talk some more about this after the session, because I'd love to hear about what your use case is for asking this kind of question. So thanks. Any other questions from the folks in the room? Okay, apparently they can't really hear us very well. So for the AV team, if we could bump the noise a little bit on the virtual stream, it would be appreciated by the folks there. We're currently not displaying anything, right? Okay, we can also show the... Oh, are you able to put that? Okay. All right, so apparently the video is frozen for some of the users. Sorry about all the hiccups here. Any other questions? Or we can also, we're happy to stick around. I think we have this room for a bit longer, past noon. So happy to also answer some of the questions in person. Samir, can we take a look at some of the DockerCon bots? Okay. Also, we've heard that the recordings will be made available next week. So here with the DockerCon bot channel, we can see some of your beautiful creations. So maybe a small recap about what we did today. So we intentionally made these labs fairly involved because all of you learned how to build a model container. And all of you have gone through the pains of what it means to build a model container, upload it on Docker Hub, then pull it from an endpoint. And if you go on OctoAI today, actually, we can help you skip that process because we've already created model templates. So you'll notice that SDXL actually is a model that you can already pull, and it'll be up and running really fast. So we can actually bypass this long process of model authoring if you go to OctoAI and pull some of these model templates from the website. And you should be up and running within seconds as opposed to what we did today, which is within tens of minutes. The other benefit of using our template is that we've actually applied a lot of optimizations to these models to run faster. So today it took about 10 seconds to run an SDXL inference using the model library that we employed for the lab, which is diffusers from Hugging Face. But if you use our cloned endpoints, you can actually run SDXL in about half that time. So much better performance, much better bang for the buck. So something to consider. And this list of model templates that you can clone from on OctoAI's website is something that will keep on growing over time. And we're getting some really interesting photos here. I saw there was a question here from the audience. Would you mind? Okay. So Luis will come and help out. So certainly, we would appreciate feedback and input. And since you've all joined this Discord channel on OctoAI, of course you can ask questions if you'd like to know how to build interesting verticals or interesting applications powered by our OctoAI compute services. Hopefully today you have a good taste of what it means to build generative AI apps in something that looks very close to a production setting. because the only thing that separates you from an actual production setting is the number of replicas that you're going to use for your endpoints here. Okay, so are there any other questions? We're at the, we're at 11:41, so we still have about 19 minutes till the end of the session. And of course, I invite people to complete their labs 1 and to refine their images and prompts and bots to get some really cool effects. And also, if you got some really cool images that you love to share on social, don't hesitate to put them on, Twitter or LinkedIn, and add the hashtags for the DockerCon events or OctoAI as well. All right. Yeah. Do you mind going to the mic so people on the virtual session can hear you?
So I noticed you had replicas that you can set. I was just kind of, if you can go into detail, like what the replicas are,
Yeah.
and then also like how do you know when to add more replicas?
Yeah, definitely. Happy to do that. So, do you have Octo? Okay, great. Yeah. So this is an excellent question. Yeah. So the idea of replica essentially is going to determine how much you can scale your service in order to provide. Sorry, one second. We just want to make sure that we were able to. Okay, can everyone see this? Okay, great. So Samir, if you go to templates, or yeah. Okay, so DockerCon 23 SDXL. So yeah, we can see that there's a number of min and max replicas, which we've set to 1. So that means that for this inference service, we're only going to have one instance with one GPU servicing the inference request. This is enough for anyone who's trying to build a demo, who's going to show it around to their colleagues or their boss or their families and friends. But if you want to run this in production for, say, tens, hundreds, thousands of concurrent users to hit, let's say you're building the latest and greatest image filter for Snapchat or Instagram, then you're probably going to be servicing many thousands of users all at once. And so changing that number of replica will allow you to scale your inference server to respond to that demand that's required by whatever at-scale service you're running. So as a developer, what's really nice and powerful here is that you can start with 1. But if, let's say, you want to start to deploy it in alpha mode to a select number of users, and then beta, early access, etc., you slowly scale the number of users that can hit your endpoint concurrently, your service. You can change this number of max replicas from 1 to, say, 10 to 100. What's nice is that we're providing a range. So that means that depending on traffic, the number of replicas will scale up and down within those bounds. So you can set the max to 100, the min to, say, 20, and you're never going to go below 20, you're never going to go above 100. So you can guarantee some availability of your service without, say, going above some of your cost restrictions of certain number of dollars spent per day or per month on your generative AI service. Okay, one more question. Please go talk in the mic.
So from my use case, I actually operate in an air-gapped environment, and obviously you're supporting from the cloud perspective.
I can't hear you too well. Can you speak more?
Sorry? Okay. Yeah, so you're obviously supporting in a cloud environment. But what alternative would you recommend if we didn't have access to the cloud and needed to host something locally? Obviously, you might have templates or just an overall alternative.
Yeah, that's a great question. Yeah, so as you notice, our service is very much focused on the cloud. But actually, many of the co-founders of OctoML came from an Edge background. Myself, I'm an Edge ML person in my past academic life. And we worked on a project called TVM. And I'm not sure if any of you are familiar with Apache TVM, but it's an open source machine learning optimization framework that gives you portability, that it gives you the option to deploy your machine learning and AI models on all kinds of hardware backends, both cloud-based and edge-based. So I would certainly point you towards the TVM or nowadays is actually referred to as MLC, the Machine Learning Compiler Project. And actually OctoML has funded a lot of growth in that open source project that allows people to run many of these really interesting models like LLMs, image generation models on the edge. So there are several demos that you can look up nowadays, like the MLC LLM project that lets you, for instance, run an LLM on your cell phone. It's obviously not the fully fledged Llama 2 model, but we use the web GPU backend to actually run these LLMs on any kind of low power SoC. And there's also some text image examples that you can play with running on the edge. And we have some really cool examples, like running things on your M1 MacBook or M2 MacBook, running ML on AMD GPUs as well, which you might have on your desktop or in other edge deployments. And actually, the commonalities between what I've shown you today and the TVM project is that we're using a lot of the TVM framework optimizations to improve our ML model templates that you can grab from our cloud website. So all those innovations in machine learning optimizations that come from this open source project, we're flowing into our cloud offering, which will give you best-in-class performance in cloud. But these are things that are open source and that you can use on the edge yourself. So depending on your platform, I invite you to check out Apache TVM, or how it's referred to nowadays as the MLC project, Machine Learning Compiler.
And also, I just wanted to add one more thing, especially when you are running these models inside a container, right? So if you are using the edge devices like NVIDIA Jetson and the Xavier, right? You can still, we have a support for Docker Compose. So you can use Docker Compose with GPUs. So if you are running on the edge devices, the commands which we ran to basically a Docker run command, it still works on those edge devices. But yes, you need a powerful GPU. I think Xavier would be the one if you really want to run such kind of models.
We probably have some time for other questions if anyone wants to ask any. And of course, we're monitoring the Discord channel in case anyone who's attending remote wants to ask a question. And of course, the team here, Luis, Samir, Ajeet, and I, are going to be around if you want to network, talk. We're happy to provide some input and advice. Okay. Well, no more questions. So we still have the room for another 10 minutes. Feel free to continue to hack away at your lab 1, complete that, or just wrap it up. Just remember to pause your endpoints if you launched any. You're not going to be billed past the free credits that you're given, but in case you need some credits to work on a project over the weekend, and of course, I'd love it if you enjoyed using OctoAI so much that you would actually like to use it for a follow-up project. We'd love to get some input. So, but yeah, if that is all, then thank you all for attending this workshop. I hope you had a lot of fun. I hope you learned a lot and you got to, now terms like stable diffusion XL or Llama 2 or model containers are not going to be as foreign as they were 4 hours ago. So thank you all for attending this workshop. Thank you for the feedback, the surveys, and the participation. And stick around on Discord if you want to ask questions. We're here to help. So, we love some of your input on how to make also this experience better, how to build better bots, what kind of models you're really interested in, etc. So looking forward to that participation in that Discord server. Thanks everyone for attending this session and enjoy the rest of the conference.